materials. I am Omar El-Shafee. This is my second time doing this FE review for strength materials, and I've been teaching strength materials for the last 4 years. So by now I learned one or two things about how it goes. So basically, this is a bit of a long session, so it's broken into different stages. The beginning is basically that I'm going to go over a very fast review for the topics, just to refresh your memories. This is not an actual test that's going to go through things, it's more just you, so you need to know how things are going. But sometimes you may need to slightly tweak some topics. That's why I'm going to do a very fast review. Then I'm going over selected problems with solutions. This will be recorded and I will share with Emilia and the people in charge the slides. Then at the end I will have questions. I'm not doing this 3 hours straight, so after 1 hour, 20 or 30 minutes, we're gonna have like a 10 minutes break. Then we can keep going. I'm here till 7, and during the process, if you have a question, just raise your hand. The people that have been in my class know how this goes. Just raise your hand and ask. I'm sure now you are less shy than when you were in my class before, because some people don't really ask. Also, there is nothing at stake here. Basically, there is. You're gonna see me today, then you just wanna wave to me the whole way afterwards. Anyway, if you feel like it. So, just to get started at the very beginning, for deformations of the axial loads, you know that if you are pulling something with a length L, with a force P, it's going to deform by a little bit delta. And from Hooke's law, knowing that sigma equal E epsilon, so epsilon equal sigma over E or P over AE, using epsilon equal delta over L, you come up with the equation that delta equal PL over AE. Usually, since this is really fundamental, sometimes you may be just asked to use this formula, but typically you may be asked for 2 sections, so your delta is the sum of PL over AE, so it's P1 L1 over A1 E1 and so on. So this is one kind of problem where you are just dealing with axial loads. This may, sometimes the formulas I'm using here may be slightly listed differently in the equations that you're going to have for the FE. So mind, this is the same thing, but sometimes it's slightly different in the nomenclature. But what matters is to understand what's going on. You are having the equations anyway. You just need to know how to use it. Alright? Also, while I'm moving on, I will ask you if you are still copying, just raise your hand. And I'm saying like I'm going to share this, so don't feel obliged to copy every single thing. But if copying some material will help you through the process, I'm totally fine with this. Any questions with this? Issues? Alright. So, anyone still copying? So basically, we go for thermal stresses. While thermal stresses is a famous kind of problem, you have to know one thing. Thermal stresses will not happen if this thing is not restrained. So this is resting on the table until you heat it, it will expand. If you freeze it, it will contract. But if it's climbing between 2 walls, it can't. It's trying to expand, the wall is drained back, stresses happen. But if there is a gap, which is a famous kind of problems, before you start putting your stress equations, make sure that this temperature is actually closing the gap. Because if it's not closing the gap, then there is no stresses. And I don't know how much is the sense of humor of the person putting the FE exam, but this can happen. Because part of the things you should first check if you are actually issue or not. We were humorous enough to put it in the strength exams, but I don't know about FE. So assuming it's fixed, or the gap is closed, and you are heating, it's trying to expand, the wall is pushing back, so it's under compressive stress. If you are lowering the temperature, it's trying to contract, the wall is pulling back, it's under tension. So either way, thermal stresses are developing. And basically, your total delta, which is equal to 0 by the way, equal alpha delta TL, which is the thermal stresses, alpha is the thermal expansion thermal coefficient, delta T is the change in temperature, and L is the length, plus the deformation happening from the opposite direction from the load, PL over AE. And since delta equals 0, this is a condition, if there is a gap, then these two are equal to the gap. So assuming that the gap is 1 millimeter and the temperature will increase by 2 millimeter, then 1 millimeter is free expansion, the next millimeter is happening for inducing stresses. So basically, this is 0 if there is no gap. If there is gap, this delta equals the gap. And solving this, you find P equal negative A E alpha delta T, or the thermal stress equal negative E alpha delta T. That's why I'm telling you, you may need to check the equation sheet to see which form of this you are getting. Because you may be getting, also if you are dividing by L, then this thermal strain. Then epsilon B equal alpha delta T plus P over AE. It's more or less the same thing, so just revise. So for stresses, so for thermal stresses, yeah, it's telling you that delta T equal alpha L delta T. So it's just giving you the thermal component. So setting this up is basically on you. I may look at this. Alright. So this is regarding thermal stresses. As I'm telling you, I'm going to cover problems on these topics, but I'm just reminding you because some of you I saw 2 years ago. And people that I saw last semester may not remember. So 2 years ago, like good luck. Any questions so far? Well, it's not gone, it's just buried in your brain. I'm trying to dig and remove some dust and get it out. Yes?
What is E?
E is Young's modulus of elasticity. Typically, this is given as a problem. It's really rare that we will ask for modulus of elasticity. Usually it's given to you and it has the units of stress, so it will be in gigapascal or PSI or whatever units given to you. Yes?
Do they ever expect us to know, like, lots of the elasticity for, like, steel, like 1,000 or something like that?
I doubt it, but when we go through the problems, you're going to see how the input is given to you. Because the same also, since the problems are MCQs, giving you, assuming that you know the E for steel, we already make the numbers sketch, so it's easier for them to give it to you. Unless the numbers are very different from each other, so even if you assume 210 gigapascal or 200 or 190, will give you the same correct answer. If you want the exact answer, the problem is going to give it to you. Other questions? Okay. Now, next is generalized Hooke's law. Generalized Hooke's law, when you have Poisson's ratio and you have interaction between the different directions. So in other words, I'm pressing this thing, so the sides are parallel. This kind of problems. Or I'm tensioning this thing, so these sides are getting thinner. Where loading in one direction is affecting the others. So you will find that epsilon x equals sigma x over E minus nu sigma y over E minus nu sigma z over E. Here, this formula is supposed to be given to you. You just need to know one thing. Contraction epsilon is negative, expansion epsilon is positive, sigma tension is positive, sigma compression is negative. Because here you will run into situations that negative is positive and all of this. So here is basically, you need to do the right mess. And the formulas are a little bit clouded, and sometimes it's even worse if they tell you that one direction is restrained. So if I tell you that this can't move in y, then tension y is 0. But this doesn't mean that sigma y is 0, by the way. So unstressed means that the stress is 0. Restrained or prevented from moving means that epsilon is 0. So you need to be careful which is which here. For shear strain, which is really straightforward, since there is no, it's independent, table equal shear out. which is the shear modulus, and gamma, the shear strain, which is like an angle. Epsilon is delta L over L. Gamma is basically the shear, like, this is gamma. This is gamma, which is this delta over this H. And gamma equal 10 gamma equal delta over H. Because it's small angle. Everything in elastic range, you can use small angle approximations for this kind of calculations. Any issues? Yes?
So just to be clear, the delta is just like the satisfaction form regardless of what.
Basically, when you are shielding something, you are applying stress in one plane, in this plane, and this plane is deforming by this angle. So usually shear stress problems, if it's given to you, it will be more or less easy problems because there is two planes, one loaded plane and one deformed plane, which is not the same plane. So these problems are usually straightforward as calculations, but since it's relying on you visualizing what's going on, this is the main thing. I have one of these in reality. Other questions? So regarding moduli, to recap this part, Young's modulus sigma equal E epsilon, uniaxial tension, shear modulus tau equal G gamma, G equal E over 1 plus 2 mu. So knowing E and mu and G, knowing 2 of the 3 can get you the third through this relation. For isotropic materials, bulk modulus K equals E over 3 1 minus 2 mu. This is a change in the volume, while P equal negative K and E is a change in volume is delta mu over V. P is the average atmospheric pressure. So E is the dilatation, the change in volume per unit volume. P is the atmospheric pressure. This part I didn't see a lot of problems over it, but I saw some things related to that.
These are also used all the time.
You were first, sorry.
These are also used for like blocking stressors for others.
Yeah.
Right.
This is mainly if you have a block loaded from different directions and you are trying to get a chicken point.
Remind me what V is in the isotropic materials equation. V. Yeah. Little v. Yeah.
And new, this is concentration.
Got it.
No, this is not V, this is new. This is V, this is new. It's a little bit confusing because some of the symbols look like each other. That's why remembering which is helpful. Other questions? Next topic is basically torsion. If you have a shaft under torsion, basically this torsion is producing shear stresses which vary linearly with radius, starting at 0 at the middle, ending with maximum at the edge. And your tau, the shear stress is 0 over J, which is any general value. But tau maximum at the edge is Tc over J, where C is the shaft radius. And J is the polar moment of inertia, pi over 2 C of R4. Tau will be very linearly with radial position, and rho is this radial distance, and C is the cross-sectional radius. And it's super famous in problems that we can give you the diameter or ask for the diameter, because this always never gets old. You need to divide the diameter by 2 if you are everything in the formula, or you need to multiply the radius by 2. And I'm almost sure if you get a question with this, one of the answers will be designed if you mistakenly use the diameter. This is one of the ways of making MCQs. I put the right answer, then I start thinking, okay, if someone made this mistake, what will be the answer? If someone does that mistake, what will be the answer? Which is the worst problem kind, because you are likely doing these mistakes here or there. When we get to the problems, I will also teach you something. You may not know what is the right answer, but you can be sure what is the wrong answer. So you can choose by elimination. So instead of choosing by a probability of 25%, if you are sure about 2 answers that wouldn't work, that was 50-50. Try not to do it with pure luck. Not the best way. Try to make an educated guess if you are trying to guess. Any problems so far? Questions? Okay. This is regarding the stresses of shear. Regarding the strains, while normal stress produces deltas, shear torsion produces shear stresses and torsion. So this is a twist angle. To get this twist angle, I'm not going to go through the proof, of course. Phi equals TL over JG, where T is the twisting moment or torque, L is the length of the shaft, J is the polar moment of inertia, pi over 2 6 power 4, G is the shear modulus. And if you have multiple ones, then your phi is the sum of TL over GJ. And do you know what is the units of this phi? Radians. So if the answers are in degree, you are supposed to multiply it by 1/8 and divide by 1. This also can be a trick because one of the answers maybe is the right angle in radians. So you have to be mindful of that. While we're teaching strengths, we introduce you a bit to these concepts in the final when we were having MCQ questions in the final, but this was a small version. Here your whole exam is based on that. So this is analogous to the axial problems. Instead of like adding deformations, you are adding to angles. But also I know that here you wouldn't go super deep into complicated problems, so you may get shaft with one radius or maximum 2 divisions. This problem is supposed to be done within 5 to 10 minutes, which means that you shouldn't be doing the same thing like 5 times. It's basically testing the concept that you know it. It's not testing how professional you are in this part. All right. Anyone still copying? Issues? Well, if you are dealing with transmission shafts, then you just need to add the power equation, where P equals T omega or 2 pi Ft, where F is the frequency of operation in hertz, pi is pi, and P is the power. Whether it's in Newton meter per second, which is watts, or kilonewton meter per second, which is kilowatts, or feet pound per second, or inch pound per second. If it's given in horsepower, which I doubt, you have to multiply by 550 to put it in feet, or 6,600 to put it in inches. And all these units per second, so the frequency have to be in hertz. So if it's given to you in RPM, divided by 60. Okay. Now we're going to shift to bending, which is starting with moments of inertia. Let me see what's given to you here. Moments of inertia. Well, it's in Shear properties probably. So you have to look to this into Shear properties, but I'm sure at least the circle and the rectangle will be given. While for the rectangle, Ix is 1 over 12 ph cube, Iy is 1 over 12 hp cube. It's the dimension parallel to the axis multiplied by the perpendicular cube. The circle Ix equal Iy equal pi over 4 r to the power 4 and j equal to I. It's really rare to deal with triangles under bending, so I wouldn't really worry about that. You should worry more about rectangles and or squares and circles. So basically the issue is not what happens to the rectangle. The issue is when you have something that's not rectangle and you need to divide it into a bunch of rectangles. This is the actual issue. When you have a T section or I section or something that you need to play with. Here is like knowing the inertia for rectangle, it's either a bit here or not a bit here. Did you find it? Yes. It's in page 74. you will find all the shapes that you need and you don't need over here for stencil materials. But what you need to notice is the following. If you don't have a regular shape, you have to divide it into pieces and rely on parallel axis here. So if you have something like this, say this one, say this two, then your centroid is in the middle axis of symmetry, but you don't know this y bar. But you know this centroid, y2. And you know this centroid, y1. So y bar equal a1 y1 plus a2 y2 over a1 plus a2. And so on. Of course, if you have four divisions, you do it more. For centroid, whenever you have an axis of symmetry, centroid line. That's why for I it's right in the middle, because it's double symmetric. For inertia, you have, so this is the y bar. You have this distance from C1 to C, T1. You have this distance from C2 to C, T2. I equal I1 plus I2, and I1 equal 1 over 12, V1, H1, Q, this X of course, plus A1 D1 squared, plus I2, which is 1 over 12, V2, H2, Q, plus A2 D2 squared. So basically, you have to define what is the centroid, measure, if you are getting IX, measure the Y distances from the division centroid to the total centroid, get D1, multiply the area of part 1 over D1 squared, plus the own inertia of the part. Of course, in Y, you're going to do the same but with horizontal distance. I don't think you will need to do this in the exam more than once, maximum twice, because this is not a torture exam. There's a lot of things to go over. And this is called parallel axis here. I'm not sure if you have actually this formula in the book or not to transfer energies. Any problems so far? Issues? Anyone still copying? Okay, we need this for bending and for half of the topics I'm going to talk about right now. So, because like for half of the topics of dense materials, you get the inertia or you're giving the inertia and find out what to do. You will find that for single bending, sigma, something like this, you will find sigma equal my over I. So if like this is the z-axis, and this is y-axis, and this is the x-axis, sigma is equal negative my over I. As an adult now, you know how this negative positive works, right? Since you have experienced this a little bit, that by now you should know that it follows. If this is Z and this is Y, if your moment is like this, then sigma x equal mc over ic y, negative. You check with the positive coordinate if it's the head of the tail of the arrow. Or in other words, from the moment the tail produces the tension, the head produces the compression. This is how it works. While this was a little bit of rocket science to say in strength of materials, now after you took concrete, you took steel, you took into structures, now you know how this works. Where your y is measured from the neutral axis and I is with respect to the neutral axis, and needless to say that the maximum compression in this case happens on the top and the maximum tension happens at the bottom. Any issues so far? Questions? In case of unsymmetric bending, you will find that it is superposition, which basically analyzing your moment into two components, My and MC, and getting to compose them as if you are as a vector, as if it's a force. So MC equal M cosine theta, My equal M sin theta in this case. And you find that your sigma equal negative MCY over IC plus MYZ over IY. Why is that? Because in the positive Y, I have the head of the arrow. And in the positive Z, I have the tail of the arrow. That's why one part is positive, one part is negative. I wouldn't really worry about this neutral axis part because this is too detailed. More important is that case. If you have something like this, let's say this is my Z and this is my Y, and I have P over here, which is tension. This means that you are getting the P over here is two moments. One moment around Y and one moment around Z. The upper left corner is in tension, which means if the moment is right-left, the head is compression is right, the tail is tension is the left. And if the moment is up-down, the upper part has the tail which is tension, the lower part has the head which is compression. And then sigma x has three parts, P over A, MC over IC, Y, MY over IYZ. This is tension, so this is positive. MC working with the Y, the head is in the positive Y, so this is positive. MY working with the Z, the head is in the positive Z, this is negative. This equation I just wrote is the general stress equation. Substitute any coordinate with its signs, you're going to get the stress right away. And it can't get worse than this, by the way. This is the ultimate case over here. There is different ways of doing it. There is right-hand rule, there is things I don't like, but this is one way it works. If you have another way to do it, I'm fine with this. Any problems so far? Alright. Now comes something you are really used to now. Shear force diagram and bending moment diagram. You know that the shear is the integration of the load, and kinetic is the integration of the load, and the moment is the integration of the shear. Basically, for shear force diagram, if you need to draw one, which by the way you may need to, some questions ask you for, or at least ask you for a value or to pick the right one, you start from the left, you go up with what's going up, you go left, you go down with what's going down. If it's concentrated load, it goes suddenly. If it's distributed load, it goes as a slope. If it's a triangular load, which may happen, it's a parabola. And it has to end with zero on the other side. For bending moment diagram, you can either take section equilibrium at points or basically calculate the area under the shear curve. And the maximum moment happens at the zero shear. While a zero shear by a load passing like this is really easy to spot, sudden load drops that gets you from positive to negative actually is another zero shear that you may not know right away. Concentrated moments. Clockwise, since you are drawing from the left, clockwise is positive jump upward, counterclockwise is negative jump downward. Anyone is drawing shear and bending not from the left? If you draw it from the right, then you have to flip all of this. But this will make shear harder to draw. Also, I doubt that you will have a problem like beam problem with a concentrated moment, because this was even harder on your fixed strength materials. Unless the person putting the exam really hits you. Any questions so far? Issues? Now comes a topic that you really don't like, if you remember the sequence of this class. Shear. If you are studying shear in nails, you need the shear flow, where Q small equal PQ over R. And Q is the first moment of area of Y1. The whole thing of shear, you need to know what's going to break. So if this part is nailed or glued and it's gonna break, like the nails over here, splits a small part from the section, gets the moment of area of this part if it will split, which is the area of that subdivision multiplied by the distance for its local centroid to total centroid. It's first moment of area. R is the inertia of the intact section, and V is the shear force. So this whole chapter is governed by two equations. Q small equal VQ over I, tau equal VQ over IT, and that's it. All you need to know is to understand what's going on, which is typically not very easy. So if you are dealing with nails, you need to get the force per unit length, shear flow, VQ over I. If you are dealing with glue or with strengths inside the material itself, you're going to need to use tau, which tau is more or less this equation, but we divided both sides by T or P, the width or the thickness of the section. Alright. So VQ over IP or VQ over IT, same exact same. You still need to cut, you still need to see what's going to split, but now we have also the width of the section, which is like the width of the part that will get cut. Here you need sometimes to sketch or understand what's going to get cut. If this is a rectangular section, then tau maximum having the Newton axis 3V over 2A, and it starts with 0 and with 0 parabolic distribution. Next topic is basically transformation of stresses. All the stresses you are dealing with here are either sigma or tau or both of them. If you need to transform the stresses, anyone see copying before I go? Okay. You have these equations, which are super unlikely to see this, to tell you transform the stresses of inclined plane. The more likely is to ask you for principal stresses or maximum shear stress, which have this version of the equation. So sigma maximum or minimum is sigma x plus sigma y over 2 plus core maximum minus core minimum, the square root of sigma x minus sigma y over 2 all square plus tau xy. And for tau maximum is the second part, the square root of sigma x minus sigma y over 2 all square plus tau xy square. The same, this equation have one issue. You need to be very mindful of two signs. Tension is positive, compression is negative. Shear, the arrows leaving in the upper right corner is positive shear, leaving the upper right corner is negative shear. And the other alternative, I don't think you're going to be asked for principal planes. This is also too detailed. The other alternative is to rely on more circle. You may not, no one will ask you to do more circle in every exam, but you may sketch it fast and get the components from it if you are not very happy with these equations. Of course, what I'm saying right now for mechanical engineers is blasphemy, but we're civils, and you took some classes that you actually used more circle. So now you know it going beyond this. I was just getting started. How many of you took experimental soil mechanics or now called technical design? How many times you drew more circle over there? I did that class 5 times, so I know it very well. That's why for me doing more circle here. Okay, you drew it too many times. Imagine how many times I graded it. So for me, like that's why more circle is like I know it like it's the back of my hand. If you are doing more circle, you are plotting the stresses where tension is positive, compression is negative, shear clockwise is positive, shear counterclockwise is negative. And basically the size of the circle, the radius of it is tau maximum, the furthest part, like the biggest part is sigma maximum, the lowest part is sigma minimum. While some of you already drew to scale several times, even with sketching and using trigonometry, that's fine. This is the other option if you don't want to use the equations. However, if we are asking you for out of plane stresses, maximum stresses, you will need to understand how our circle works. Because basically all these circles represent what's happening in the XY plane. So if I give you sigma z, you need to draw one circle with sigma z and sigma minimums, one circle with sigma z your maximum, and the largest of the three circles is your maximum out of plane stress, which in that case happened to be one of the out of plane Moore circuits. Any questions? While in this case happened to be that the in-plane Moore circle for sigma z equals 0 was also out of maximum out of plane. So this may happen, but the thing that will most probably happen, because I saw its questions multiple times in FE, is thin-walled pressure vessels. If you remember anything about thin-walled pressure vessels, if you have a cylindrical gas tank and there is a pressure inside, you try to push it open, there is hoop stress and there is longitudinal stress. And the equation for hoop stress, PR over T, where P is the pressure of what's inside, R is the internal radius from the center to the wall, inner center of the wall, T is the thickness of the wall. Sigma 2, the longitudinal stress, is PR over 2T. So sigma 1 equal to sigma 2. In case you, and basically you will find that the maximum in-plane shear stress is sigma 2 over 2, while the maximum out of plane shear stress is equal to sigma 2. Because it's between sigma 1 and 0, and sigma 1 over 2 equals sigma 2. In case you are dealing with a cylindrical vessel, which also can happen, you have this, but it's a twist. But before I go there, any issues so far? Questions? So if you are dealing with a spherical vessel, there is no sigma 1. It's all longitudinal stress. So sigma 1 equals sigma 2 equal PR over 2T. And in plane, your circle is this red dot. So the only source for shear is out of plane shear stress, which is equal sigma 2 over 2, or PR over 40. Any issues? The next part I'm going to talk about is a little bit formality, because I didn't see problems about it, because it's transmission shafts and combined loading, and this is beyond ridiculous to ask in MCQ. You have a lot of things to cover on fundamental basis here. Regarding transmission shafts, the design equation said J over C minimum is equal to the square root of M squared plus T squared maximum, the maximum combination of winding moments and torsion. Because basically it's like this. This thing is bent that way, under torsion. So we are trying to get the maximum combination divided by the allowed J, and then J over C minimum. J is function of C, J is pi over 2 6 over 4. So we get the C. But I doubt this will happen. For combined loading, the combined loading problems, simply you have two sources for stress. There are things producing sigma and there are things producing tan. Sigma will happen from P over A or My over R. Tan will happen from Tc over J or from Vq over It. If this happens, you are trying to get this and then like get some maximum stress or minimum stress. But this, if this happens, the problem will be half prepared for you, which means that it's more or less like Moore circle problem. That's why I doubt that this whole problem will come in MCQ, because this will take like ridiculously long time. You can't really compress the MCQ. Maybe part of it. Maybe tell you, get me the combined action of these two or these two, maybe. Which is not that bad of thing to calculate. But to go all the way, problem. Now, I'm about to go to the pure civil engineering applications in strength materials, which is beam deflection and column bucket. Any questions so far? Issues? Regarding deflection, if you integrated
the moment you get the slope theta, if you integrate the slope, you get the deflection. There is really or almost no chance of getting integration. You will be actually dealing with superposition. Do you remember superposition? Superposition basically you have cantilever beam under concentrated load, or cantilever beam under distributed load, or cantilever beam under moment, or simple beam under distributed load, simple beam under a load in the middle, simple beam under a load not in the middle, simple beam at a moment at the edge. And your whole job is to devise your problem, whether it's statical or determinant or indeterminate or indeterminate, to punch with these problems so you can use the tables which are on your book. I just saw them for mechanics material. No, page 90 and 91, where you have the slope, the deflection, and the elastic curve equation. So basically, getting any problem, general problem, if you are able to divide it into these two cases, for example, this is beam under distributed load, this is beam under concentrated load, then you can get the maximum deflection at a specific point, depending on what is requested from you. This is more or less what you have here, a little bit different formatting, but basically, it gives you the case, it gives you the shape of the elastic curve, it gives you the maximum deflection, and its position in case it's not very well known, and give you the slope at the end, and it gives you the elastic equation of the elastic curve. Equation of the elastic curve is going to give you the deflection anywhere. But if this deflection is the maximum deflection or a famous point, there is no use, good use for this, because you're basically inventing the wheel. However, if the point is not a famous point, you have to use this. Sign convention. Deflection down is negative, deflection up is positive. Slope clockwise from the original beam's deflected beam is negative. Slope counterclockwise is positive. And if you forget all of this, compare this with this drawing. Because we are drawing the beam for you. So if you just forget it, just look to know what's going on. So basically your job is to make good use of this, which you have a similar version of it over page 90 and 91 in your book. Any issues? Questions? Okay. Last topic. Euler's formula. Basically, Euler's formula is prepared for hinged column, where P critical equal pi square E I over L square. However, you can extend it to other conditions just by figuring out L effective, which is this arch length. So if it's hinged, L effective equal L. If it's fixed free, L effective equal 2L, where L is actual length. If it's hinged, fixed, L effective equal 0.7L. If it's fixed, L effective equal half L. So and here you need to know that basically this is the issue. If this is your column, so this is B and this is H, and say this is X and this is Y, and this is Z. So what is Ix will be 1 over 12 BHQ. Iy will be 1 over 12 HPQ. This column will buckle this way, which is in the XZ plane. Iy. You have to, sorry. Iy. If you are buckling this way in the YZ plane, then P critical equal EIX. This is over L effective squared. So basically, the worst trick that happen here is that you don't know which I to use. And if this is a question in the exam, be almost sure that one of the combination has a wrong I. So you have to be careful with this. This is basically the only trick. This is very easy. You have the formula. These cases are not even hard to forget, to remember. I don't know if you have it here or not. Well, if you want to see it, that's fine. That's fine. Maybe I have another case, but never mind. All right. Any questions so far? Issues? All right. Let's do some examples. I will do some examples for about like half an hour, then we're gonna take a break, and we're gonna like continue more examples. Some of you may relate to this, given that you're civil engineers. Okay. Any issues so far? Yes.
So you said that for superposition and like deflection, rotation of the beam counterclockwise is considered positive.
And clockwise rotation.
Okay. But then,
From the original position to the rotating position.
yes.
So if you look at this table, it's telling you that the slope over here is negative because it's going clockwise.
Okay. So then earlier you said that for like pure bending moments, clockwise is positive.
No, this is for not for pure bending. For pure bending, you look at the head and the tail of the arrow and the axis. For bending moment diagram, concentrated moment clockwise is positive jump, counterclockwise is negative jump.
Okay.
The issue that sign conventions sometimes get conflicting depending on who's saying what.
Okay. So do those conflict at all, like about the clockwise positive for those jumps? And
Well, it's clockwise positive and counterclockwise negative because you are drawing from the left side.
Okay.
If you are drawing from the right side, it's
Yeah.
opposite.
Yeah.
But then you have to flip the sheet sign convention, it's harder.
Okay.
Because you have to go opposite, come down and vice versa.
Okay.
Good. Other questions? All right, let's start. The shear diagram for a particular beam is shown below. All lines in the diagram are straight, the bending moment at each end of the beam is zero, and there is no concentrated couples along the beam. We are giving you shear force diagram, and we want the maximum bending moment. Where are my candidates for the maximum bending moment? Yes.
Oh, your hand goes up first.
Oh yeah, it could be any one of the zeros. So
1, 2, 3. So basically, if you are looking at this area, it's 14 plus 12 over 2, which is 13 multiplied by 2 is 26. So probably this is the answer. Because if you go here, 4 by 4 is 16, which is another one, but this is the answer.
yeah.
The same here, this is not very complicated given that you can actually visually get the areas over here. Because this probably is less because it's negative 26 plus positive whatever. So this already gonna make it small positive number or a less negative number to ask for the maximum magnitude. We took you out of the issue of the negative moment is bigger or the positive moment and all of that. Because basically this is more practical. A moment will produce tension and compression. Positive and negative just telling you which side is which. That's basically it. Any questions? Here is the explanation for this answer, but I'm just letting you know what are you dealing with. And as you see, this problem is half a problem because we already drew the shear force diagram for you and asked you for the maximum bending. Okay. Another one. The pressure gauge in an air cylinder reads 1680 kilopascal. The cylinder is constructed of 12 millimeter rolled steel plate with an internal diameter of 700 millimeter. The tangential stress inside the tank is almost nearly what? By the way, what is the tangential stress? Open longitude. What? Oh. So basically, what you are dealing with is the following. Sigma hoop equal PR over T. This P is 1.68 megapascal. T is given to you as 12 millimeter. So T is 12. R is basically, well, there is a debate here because you could just use 350, but some people say R is R outer plus R inner over 2. Either way, when you do this calculation, you're going to get a number close to 50. The answer is 50. By the way, sometimes that's why I tell you it's most nearly. So they are already covered from the fact that if you use 350 or use 356, doesn't really matter. Because the answers not like 50 and 52 and 48. Like the answers are already well spaced that if this is your only issue, you're going to get 50 anyway. Sometimes they don't want to make the numbers silly, so they tell you it's closer to. So also be sure that you are already know that the answer will not be exact and you are picking the nearest number to it, which may happen. Especially if they tell you most nearly. So they already know it's not this number, it's something close to it. Any issue? The answer is 49.8. And if you try with 350, the answer will be like 49.7. So either way it's 50. The answer is B. Any questions? So far, do you feel these problems are impossible problems? They are straightforward problems, but they are playing on the fact that they don't have answer. Basically. And while it's not very fair to assume that you remember everything, you try to remember as much as you can. Is there a popular section for you that you prefer, you feel that you will not do well in it? Or not really? For FE exam? Or you're gonna try whatever you have in front of you? Anyway, this is just a rhetorical question.
I think are you asking, is there like a particular section we're worried about? Or?
Yes, it is a section that you are worried about that you feel that okay, like probably you're not gonna do well in this because also you are not grading section by section, you are grading your own score.
Yeah.
So even if there's a section that you don't remember anything about it and you just wanna go and choose all P or something, other sections will balance it out. That's why you need to see either you are trying to put effort in everything or you are reinforcing your efforts in the things you know more to get a better score to balance the things that you don't know.
Or different equations?
Not surprised. All right. Any questions? A shaft of wood is used in a certain process. If the allowable shearing stress parallel to the grain of the wood is 840 kilonewton meter square, the torque is transmitted by 200 millimeter diameter shaft with the grain parallel to the neutral axis most nearly what? What kind of problem is this? When you read this, what kind of problem is it? What? Transformation? Transformation?
It's like stress to...
Well, no. Here, I'm giving, what is this stress? It's shearing stress, it's tau. And I'm giving you the diameter of the shaft, and I'm asking for the torque. This is a torsion problem. Tau equal TC over J. Here is the same. Part of your issue that you may get thrown off by just reading the problem. You need to focus on what we are giving you and what we need. So basically, this problem, tau equal TC over J. Tau is 840,000 Newton per meter square. I'm talking in pascals. And what is your radius? 100 millimeters or 0.1 meters. And this is pi over 4, sorry, pi over 2.1 to the power 4. If you solve this, you're gonna get T equals 1319 Newton meter, which is this answer. I'm sure that if you try to substitute this equation was 0.2 instead of 0.1, you will get one of the other answers. So this was basically a shear stress, torsion shear stress problem. Tau equal Tc over G. I give you C, I give you tau, I'm asking for T. Direct substitution, just have to be careful. The solution provided for this problem used T over 2 and pi T to the power 4 over 72, which I find more complicated. It's better to use C and pi C to the power 4 over 4 over 2. Pi over 2 C to the power 4. Alright. Any problems? Questions? Another example. The piston of a steam engine is 50 centimeters in diameter. If the maximum steam gauge pressure is 1.4 megapascal. If the design stress for the piston rod is 68 megapascal, its cross-sectional area in meters squared should be most nearly what? What are we doing here? What is this problem? What's going on here? I have a piston. The piston have a diameter that you know, and they have a pressure that you know. Now there is a rod connected to this piston with a pressure you know, sun stress you know, but an area you don't know. What is the constancy here? The force going through is the same. The force that pushing goes is the same. So basically this problem, while it's not exactly your kind strength problem, it's more like this problem. P equal P. P1A1 equal P2A2, basically. So, the F rod equal PA or equal 1.4 times 10 to the power 6, because they want this to be in meters, so we're going to work everything in pascals. Multiplied by the area, which is pi times 0.25 squared by r squared. This is equal to 68 times 10 to the power 6 multiplied by the area you don't know. If you do this calculation, you're going to find the area 40.4 times 10 to the power -4 meters squared. So basically your answer is E. The issue here is that the wording of the problem may throw you off a bit because it wasn't very clear, but saying that if you have a piston and a piston rod, these are two things connected together, moving together, carrying the same force together. This is basically as more simpler than you think, but it just sounds complicated. Any issues? And as you see, the solution is actually confirming what I'm saying. Like the F rod is the same. So basically multiply 1.4 times the area give you F rod, which by the way you don't even need to get, because you can simply equate these two together and make A. You don't even need to do the intermediate step. Sometimes FE exam have conceptual questions, and conceptual questions happens to be torsions. Which is the following is true when a circular shaft is subjected to torsion only? It is the same. I have a shaft only under torsion. Will this ever mean that there is no shear stress present? Of course not. This torsion is actually producing shear. So this is out. Now, if you remember what I said, the shear is linear, the distribution is linear. So constant shear is also long. By the way, there is nothing called constant shear. Even for both subunits, we assume it to be constant. It's either linear or parabolic for anything. It's never constant. So it's either A or B. Maximum shear occurs at the outermost fibers, or maximum shear happens at the center of the shaft. If you remember what I just said, center of the shaft has zero shear. The maximum happening at the outermost fibers. So you need here to work with the approach. If you remember this, good for you. But if you don't remember this, start with what doesn't make sense. It doesn't make sense that you are torsioning this thing and there is no shear present. This will happen if it's not loaded. You may confuse what is the distribution of the shear, but you know that there is nothing as constant shear. We may approximate it constant. This is a real. Now you need to know that it's linear from 0 to the edge, not vice versa. But at least now you knock down two things that doesn't make sense. Make sense? Still good? Alright. Now 1 feet rod with a diameter of 0.5 inch is subjected to tensile force of 1,300 pounds and has elongation of 0.009 inch. The modulus of elasticity of the material is most nearly what? Here. What kind of problem is this? Yes. Yeah, delta E over P L over A and L in E. So basically, this problem, delta equal PL over AE. Delta is 0.009. P is 1,300 pounds. By the way, I can't use really 1,300 pounds. I better use 1.3. You know why? I asked for E in KSR. So I should put everything in inches and the loads in caps. Another issue is units consistency. But fortunately for you, there isn't something blown up by 1,000 up or down. So if you got the number right, probably you know that you messed up 1,000 or 1,000,000 somewhere and you're gonna get the right answer. If this is your only issue. What is the length? 1 feet, have to be 12. This is the issue. The issue is that you have to make the length in inches. What is the area? Pi 0.25 square. If you solve this equation for E, you're gonna get E equal 8,840 kPa, which is answer C. So here you just need to be mindful to your units. If I were you, I would start with loads in kips and make everything in inch, because we already give you a tip. The units in KSI. This is common. We're gonna give you the unit. You handling the units is your problem. And it's famous that people are allergic to units because they just put the numbers as they are, and in English units, it gets worse because the feet is 12 inches. So it's not just the issue of zeros. The issue may be a little bit harder than this. That's why I have to be careful. All right. Okay. Any questions so far? Another problem, which is a fun problem. The maximum in plane shear stress in case I in the element shown below is mostly irrelevant. In these problems, it's almost impossible to mess up with units. Everything will be in case I or PSI. Here is the issue is beyond units. What do you think? If you look to this problem, what do you think we should do here? First of all, what am I looking for? If I'm telling you plane shear stress, this means I'm looking for the radius of Morse circle. So you either sketch Morse circle or use the equation. If you decide to sketch Morse circle, this is what you have. You have 20 and negative 10. And you have 20 and positive 10. And you have 40 and negative 10. Which means that your center is at 30. Which means that your radius, the square root of 10 square plus 10 square, the square root of 200, which is 14.1. The answer is B. If you apply the equation is actually giving you more or less the same result. Any problems so far? Issues? Yes.
There was 20 and 10, 20 positive.
This is, yeah, well,
The first one.
yeah. This is 20 tension and half shear, which is clockwise, so it's positive. Here, this is 40 tension and half shear, which is counterclockwise, which is negative. But here, since you are looking for the sides of the circle, even if these two got flipped, you still don't get the answer. And the explanation here is actually giving you your radius. And the answers was already well spaced, like 10, 14.1, 44.1, 36, which accounted for just getting the distance without getting the square root, assuming one is tension instead of compression instead of tension, all this kind of common things. All right. Any other questions? Issues? Yes.
Have there ever been any, because it says in the FE practice exam that it's only under the materials section where you have a more circle problem. Would you see any of them in the geotechnical section or any others potentially?
Probably not.
Probably not. Okay.
Who's doing the geotechnical section? Victoria?
Sorry.
Victoria Bennett, who's doing the geotechnical? You can verify with her, but I have read the book before and I know in geotechnical sections there's a lot of other things to ask you besides Morse circle.
Yeah. Okay. That makes sense. Just
Other questions? The Euler formula for column deals with what? Relatively short columns, shear stress, tensile stress, elastic buckling. What do you think? T, elastic buckling. You don't really need to be an expert to know this one. Alright, so now I will give you 10 minutes break. So since it's over here, relax for a bit, then I'm gonna carry you, I will continue more problems, then we're gonna open questions.